Okay, today's video is the next part of the run-through for this Edexcel linear exam for A-level. So it's the Pearson Edexcel Physics Advanced Paper 2, also called Advanced Physics 2 like this. Okay, so this is equivalent in year 13 to Unit 5 of the IAL. And I know the IAL students, the International A-Level students, took their exam yesterday. So it's a shame I didn't manage to upload this next part, but it's just because of a shortage of time. But this will be there for future students who are doing it for the International A-Level as well. So each part is, I'm doing slowly because I'm trying to keep my videos below 20 minutes ideally. And today's run through goes through simple harmonic motion. So simple harmonic motion, or the topic is oscillations, is identical in both the syllabuses. So the international and the linear exams cover the same content, 99%. Okay, so let's go straight into it. So if you haven't seen the other parts, so I think this is part 5. Okay, if you haven't seen the other parts, they're all in the same playlist if you're following the linear course. Okay, so have a look at those as well, and if you find them helpful, then please show your support for my channel by liking each video that you found helpful, and share it with any friends, especially if they're doing linear, because most of my subscribers are following the modular exam, and I'm expanding to cover both. Okay, so this is from the oscillations topic in year 13 of both syllabuses. Okay, and it reads as follows. The suspension system in a car includes a spring attached to a wheel. So you could consider the wheel as the mass. So it's a spring mass system. Yeah. So if you know that if it starts oscillating, the suspension system could oscillate, then it will be T equals 2 pi square root of m over k. So that's the underlying equation which you'll find on the formula sheet. So it says the mass of the car, when it's stationary, the mass of the car is 1100 and it's stationary. So we know the total mass. Each spring is compressed by 152 millimeters. Okay, so the alternative to extension is compression, and that would be a way of working out the stiffness of the spring. Okay, then each of these springs are taking a quarter of the weight of the car. Okay, each spring is well within the limit of proportionality and the elastic limit. Okay, so they're just giving you that as extra information, and they just want you to give the standard definition of what it means to be within the elastic limit. Okay, that means in everyday speak, it has not exceeded the load which, when removed, would lead to permanent deformation. Okay, so there will be no permanent deformation at the extension or the compression that we're talking about. So how do you define it? So within the limit means, within the elastic limit, it means removing the load would return the spring to its original length. Okay, so it's in its elastic phase, and that's basically what you got to explain. So similar to GCSE. Okay, now the next part, they wanted to show, so show that means mathematically prove it, that the stiffness of each of these 4 springs is about 18,000 newtons per meter to 2 significant figures. Okay, so you just use the stiffness equation for springs, and you make K the subject of the equation. The weight on each spring, of course, is a quarter of the mass, so this is the mass. Yeah, you want the weight, so you multiply by G, mg, and divide it by 4, so you get a quarter of it, because that's what they said. Each wheel takes the same weight. Okay, then you divide it by the extension, which you need to make sure you've changed to meters. Okay, so it's all given to you, and when you just put in the calculator, you get a nice easy 3 marks. Yes, that's the accurate calculator value, if you like, and this is approximately 18,000 to 2 significant figures. And that shows that you have shown that what they've asked. Okay, so always finish off the question by explaining that you've now answered the question. Okay, other people write QED, which is Latin for I have demonstrated what I set out to demonstrate. Okay, I think. All right, so the next part, just take a sip of coffee and I'll get to it. It says a force is applied, which results in a further small compression. So as well as the weight, they're applying a force, so it's going to possibly cause it to oscillate. There we go. Yeah. So the force is applied momentarily because it then says the force is then removed and the body oscillates with simple harmonic motion. Okay. So simple harmonic motion means that this equation is the defining equation for simple harmonic motion. Hopefully you recognize that. They want you to determine the frequency, and you know the period can be calculated using the equation I outlined at the beginning of the run-through. So once you know this, you know the normal weight when it's removed. So it's basically you started to oscillate it, so you've basically displaced it from its equilibrium position. And its equilibrium position would be when there was no extra force added. So it will be 1100 divided by 4, the weight on each suspension, divided by K, the mass, I should say, not the weight. The 1100 kilograms divided by 4, and you'll see that that would create the oscillations into 3 significant figures of 0.783 seconds. And all you've got to do is inverse that. So you put it to the -1 on your calculator and you get to 3 significant figures, 1.28 hertz, which I think you should quote to 2 significant figures, which would give you 1.3 hertz. I think 3 significant figures will be fine. It then wants you to, and this is very common, so in all of these papers they will want you to know what the conditions for simple harmonic motion are, which I told you is the defining equation for simple harmonic motion, is where the acceleration is the negative of the displacement multiplied by the constant omega squared. Okay, so you've got to say in words that the acceleration is proportional to the displacement. You don't put it in the algebraic terms that I've used. You need to write it out. Check the syllabus to see what keywords they want you to include. Check the mark scheme. I'll show it to you on the screen in a minute. And the acceleration is always in the opposite direction to x, which is why there's a minus sign. Okay, so the minus sign shows that the vector acceleration is always in opposition to the displacement. Of course, if you pull something to the right, yes, like a pendulum, it will accelerate to the left. If you pull the pendulum to the left, it will accelerate to the right. So it's always going to be accelerating in the opposite direction to which you displace it, from which you displace it, because it's always trying to get back to the equilibrium position. That's what simple harmonic motion is. It's a way of restoring the equilibrium. So this comes in every exam, Unit 5, international students, and linear for paper 3. Okay, so it's always towards the equilibrium position. Remember that. So these are key things that you should include when you want to get the 2 marks, and you can have a look at on the mark scheme to see if your wording gets the ticks. Okay. Part D, this is the last part of the question, reads as follows. The oscillations are heavily damped by a piston. So you've got a piston here in the suspension system. So they've changed it from being a spring to being a spring attached to something which is got oil, which is absorbing some of the vibration. The piston moves within a cylinder with oil as shown, and the oil has its viscosity, and the viscosity is high, so high viscosity will mean heavy damping, light viscosity will mean light damping. So for example, honey has higher viscosity than water. Okay, so they'll use a viscous fluid. They then say, explain why using oil of high viscosity will produce heavy damping. So I've kind of already given you a clue as to that. So high viscosity will mean large resistive forces against the oscillations. So these forces are actually working against the motion. So they're trying to reduce the motion. Yeah, so the resistive forces are working against the energy of the system. So this leads to, let me just change the green, I like to do my answers in green. So this leads to a large amount of work done by these resistive forces. And you can say the work done is force times the displacement. Yeah? So just to show that you know the mathematics involved. So energy of the oscillation, the kinetic energy, the motion, is dissipated by this work done, by this mechanical energy transfer to the oil quickly. And eventually that will mean that these frictional forces will cause the oil to heat up. So basically you're converting kinetic energy into thermal energy in simple terms. And the method is mechanical energy transfer, if you want to do it as a GCSE concept. And I think that's quite helpful to go back to the GCSE concept that you may be familiar with or you may have forgotten. So the language available is slightly different from the language of GCSE. So that was my last sip of my cold coffee. So this is the final part of the 12-mark question. It's the only question in the structured section of this paper on simple harmonic motion. Okay, you'll find the difference between the linear and the modular is that modular, because they're only concentrating on the year 13 content, can give you more than one question on each of the year 13 chapters or topics. Whereas because the linear students are also examined on 2 years of knowledge, that means they also have to know about materials, and so viscosity, for example, is from materials, so they're linking it. Yeah, they also need to know about materials from year 12, and they need to know about waves from year 12. So the oscillation links in well with materials, yeah, and the astrophysics, cosmology, links in well with the waves and spectra. So you do need to make sure, if you're doing the linear, that you have got all of the year 12 knowledge from these two topics. Okay, so here's the syllabus. I keep saying syllabus. Here is the mark scheme for question 16, which I think you could just about see if I turn off my pen, all in one view with their calculations. So there's just one typo in the bottom that says may refer to work done being as force times distance, which I referred to, okay, in the final question. So I think it's self-explanatory. You can stop the video and have a look at it. Don't forget to show your appreciation, like the video, share it with any friends or classmates who you think will benefit from becoming a subscriber to my channel. And make sure you're a subscriber yourself so you can see when future papers are uploaded. After this run through of this paper, I'm going to concentrate on practical skills, and I'm going to do one for the modular next on Unit 6, which is the equivalent of the synoptic paper in linear, which is paper 3, where you have a 2.5-hour paper. They already did a 1 hour 20 in year 12, so this is the second half of that, and it's the same kind of questions. So it's worth linear and modular looking at each other's papers. Certainly linear should look at modular, because there are 3 exams per year for modular. Okay, well, thanks for watching. Hopefully catch you in the next video. Bye for now.